In the previous lecture, we proved the following result. Suppose M is an oriented manifold and S1 and S2 are compact oriented submanifolds which meet transversely. Then we can give S, which is the intersection of both these, an orientation such that the cohomology class eta S is equal to eta S1 by eta S2. So let us see some applications of this. Let P and C denote complex projective space. So we know that Hi is 0 if I is odd and Hi is R if I lies between 0 and 2n and I is even. So let us compute the ring structure on cohomology. So proposition, before that we want to prove this proposition. So every complex manifold is orientable as a smooth manifold. So proof, the definition of a complex manifold is the obvious one. We start with open sets UI in Cn and glue Uij with Uji using holomorphic maps. Phi ij which satisfy the cocycle notation. So let P in M be a point. So let us give an orientation to TPM. So this is the tangent space of M, where we consider M as a smooth manifold. So first, choose any set of holomorphic coordinates at P. So let's call this Z1 up to Zn. So we write Zj equal to xj plus iyj. Then xj, yj's are real coordinates on M in a neighborhood of P. So we claim that dx1 wedge dx2 wedge dot dot dxn wedge dy1 wedge dy2 wedge dot dot up to dyn gives an orientation on TPM. So let us check that this. So we need to check that if we take another set of holomorphic coordinates, then we get the same orientation. It is independent of the choice of holomorphic coordinates. So suppose we choose coordinates w1 through wn, then wj is equal to xj prime plus I times yj prime. Thus we get real coordinates x1 prime, xn prime, y1 prime, yn prime. And let us compute the coordinate change matrix. So since each wj is a holomorphic function, of the zi's, they satisfy the Cauchy-Riemann equations. So let us recall these equations. Suppose f from u to c is a smooth function, where u contained in C is an open set. then f is holomorphic. So let us write, okay, so let us write f is equal to u of x comma y plus I times v of x comma y. Then f is holomorphic if and only if it satisfies the two equations du by dx equal to dv by dy and dv by dx is equal to minus du by dy. So let us fix all except zi. So we fix all coordinates except zi. Except zi and view wj as a holomorphic function of zi. Then we get dxj prime by dxi is equal to dyj prime by dyi and dyj prime by dxi is equal to minus dxj prime by dyi. Thus, the coordinate change matrix where we write d by dx1, d by dxn, d by dy1, d by dyn in terms of d by dx1 prime, d by dxn prime, d by dy1 prime, d by dyn prime looks like so. In the first column we write d by dx1 in terms of d by dx1 prime dot dot d by dxn prime comma d by dy1 prime dot dot d by dyn prime. So this is d by dx1 prime. So this goes on till d by dx1 prime by dxn. So this is the nth column in which we are writing d by dxn in terms of d by dx1 prime through d by dy1 yn prime. And now we do the same for t by t by 1 and so on. Oops, this y1. So this matrix is of this type because of the Cauchy-Riemann equations. And exercise, show that this matrix has positive determinant. So because of this, this will imply that dx1 wedge dxn dyn is a positive multiple of dx1 prime wedge dxn prime wedge dy1 prime. So this implies we have given an orientation on M. So next we want to give a holomorphic structure to the intersection of two holomorphic submanifolds which meet transversely. So let's quickly do that. So first recall what is a holomorphic tangent space. For a complex manifold M, and a point P in M, define the holomorphic tangent space. As the space of C linear derivations on germs of holomorphic functions at P. This is very similar to the case of smooth manifolds, to the smooth case. And we leave the details to the reader. So let us see that the intersection of two holomorphic submanifolds meeting transversely is a holomorphic submanifold. So recall how this is done in the smooth category. Suppose X is a vector field on a manifold M, on a smooth manifold M, and P is a point in M. There is a neighborhood V of P and epsilon positive and a smooth map F minus epsilon epsilon cross V to M such that for all Q in V, we have f of 0 comma q is q and f lower star of d by dt at t comma q is equal to the vector field at the point t comma q. And if we fix q in V, then the curves and the curve minus epsilon epsilon f restricted to qm is called the integral curve. Of x through q. So the above follows immediately from the following existence and uniqueness theorem. in ODs. Let U contain an Rn be an open set and I contain an R be an interval. Let f1 through fn be smooth functions on U. Then for each point P in U, there is a neighborhood V of P and contained in U, and an epsilon positive and a smooth function f from minus epsilon cross V to U, such that f restricted to 0 cross V is identity of V, and 2 dfi by dt, the point t comma q equal to fi of f of t comma q. So suppose S contained in M is a submanifold and let P be in S. Let x1 through xr be coordinates on S at P, and extend this to coordinates x1 through xm on M at P. Then there is a small neighborhood V of P and a map V cross minus epsilon to the M minus R to M, defined as follows. So take a point Q comma T R plus 1 up to Tm. So we start at the point Q, and for time Tr plus 1 we flow for time Tr plus 1 along flow defined by xr plus 1. So we reach a point Q1. So then at Q1 we flow for time Tr plus 2 along flow defined by xr plus 2. and then we reach a point Q2 and we flow for time tr plus 3 flow for time tr plus 3 along flow defined by xr plus 3 and so on. So notice that we have fixed the vector fields xr plus 1, xr plus 2 up to xm in a small neighborhood of P, and we can choose a smaller neighborhood V of P such that flows for these vector fields are defined, and then we are flowing like this. So the image of the differential of phi at P contains at Q P00 contains x1p to xmp, and so phi is a diffeomorphism in a small neighborhood of P0. So now look at the projection, compose phi inverse. So this shows that there is a small neighborhood U of P and a submersive map from U to U prime is pi, which is contained inside R M minus R, such that pi inverse of 0 is equal to S intersected U. So if we work with two submanifolds, S1 and S2, which meet transversely, then we can find a neighborhood U containing P inside S1 intersection S2 and a submersive map pi 1 cross pi 2. So we will have submersive maps pi 1 and pi 2, but in this case the product is also going to be submersive because S1 and S2 meet transversely, such that S1 intersection S2 intersection U is equal to so this gives S1 intersection S2 a submanifold structure. So The discussion in points 1, 2, and 3 generalizes to holomorphic situation. So where we replace the tangent space with the tangent space is replaced by the holomorphic tangent space. Holomorphic vector fields holomorphic ODE holomorphic flows, etc. So a nice reference is the book called Lectures in Analytic Differential Equations by Ilyashenko. And Yakovenko. Chapter 1 of this. So thus we get that when two holomorphic submanifolds meet transversely, the intersection is a holomorphic submanifold. In particular, it being the intersection being a complex manifold, it carries the orientation we described. So let's make a remark. When we talk of orientation, on a complex manifold, we view it as a smooth manifold. So the top exterior of the tangent bundle is a line bundle with fiber R. Of course, in analogy with the smooth case, we have the holomorphic tangent bundle that's denoted TM holomorphic, and we can take top exterior, dimension of M as a complex manifold, TM holomorphic, and this is a line bundle, holomorphic line bundle. In particular, the fibers are comp C. So here is a check which is left to the reader. When S1 and S2 are oriented so before check, let's recall what we did. Are oriented submanifolds of an oriented manifold M then we gave the normal bundles in SI over M an orientation. We gave the structure of an oriented vector bundle, which in turn gave rise to an orientation on n S over M. So here we assume S1 and S2 meet transversely. And S is the intersection, S1 intersection. So the orientation on n S over M is given as orientation. Okay, so let's just recall. So n S over M is equal to n is isomorphic to n S, direct sum n S2 over M S, and we give it the orientation determined by orientation on n S1 over M, which orientation on n S2 over M. And the orientation on n S over M gives an orientation on the tangent bundle of S, which is exactly the same as an orientation on S. So check that this orientation is the same as the orientation on S coming from the complex structure. When M, S1 and S2 are holomorphic and S1 and S2 meet transversely. So in this situation, when M, S1 and S2 are holomorphic and S1 and S2 meet transversely, the intersection S is a complex submanifold and therefore it carries an orientation. And on the other hand, M, S1 and S2 are all oriented, and therefore in the previous lecture we gave an orientation on the intersection S, and both these orientations, they coincide. So in view of this, we get that the class of S, in view of this and what we saw in the previous lecture, is equal to class of S1 intersected with class of S2. So with this preparation, we are ready to come back to what we started with. So which is we want to find out the ring structure on the Grassmannian. Not Grassmannian, sorry, projective space, cohomology of projective space. So let L1 and L2 denote any two linear subspaces of codimension R. So that is real codimension 2R. Let N be a linear subspace of codimension N minus R, which meets L1 and L2 transversely. So this implies that L1 intersection N is a point because they are linear subspaces, and L2 intersection N is also a point. So since L1, the classes of L1 and L2 are in H2R, Pn, C, R, which is isomorphic to R. Let us write L1 is equal to A times alpha and L2 is equal to B times alpha for some non-zero class alpha in H2R. Then we get the class of L1 wedge class of n is equal to A alpha wedge class of n. This is equal to the class of a point, which is equal to the class of L2 wedge n, which is equal to B times alpha wedge n. So since the class of in particular, so this implies that alpha wedge n is not equal to 0 in H2n B and C are, since the class of the point is non-zero, and this also implies that A is equal to B. So since any linear so before that, so what this means is that all linear subspaces A is equal to, so this implies A is equal to B and they are non-zero classes. So this implies all linear subspaces of codimension R have the same class in H2R, B and C R, and this class is non-zero. Non-zero. So since any linear subspace can be written as an intersection of hyperplanes, this implies that the cohomology ring is exactly equal to where T square denotes the class of a hyperplane and T to the 2R is the class of a linear subspace of codimension R. So let us make a remark here about orientation of a point. So there's something which we have already used, but let's just emphasize it a bit more by comparing the holomorphic situation with the real situation, with the smooth situation. So orientation of a point is just a sign, plus or minus. So in the holomorphic case, this sign is always plus. However, this is not true in the smooth case. Let us see an example. Let T S1 cross S1 be the torus. And let X denote the local coordinate on the first factor, and Y the local coordinate on the second factor. So we fix the orientation d by dx wedge d by dy on T. So let S1 be the submanifold S1 cross 1, and so here's a torus. So this is S1. And we take S2 to be this circle. So on S1 we give the orientation dx like this. So on here we have the orientation dy, and on this S2 let's take this orientation. So let this point be P1 and let this point be P2. and we want to compute the signs that P1 and P2 should get. The local picture in a neighborhood of P1 looks as follows. So this is dy, this is dx, this is s1, and this is s2. This is the point P1. So we have a short exact sequence ds1, zero, and so this shows that determinant Tm P1 is homophilic to determinant ds1 P1 tensor determinant n s1 over m P1, and on this we chose the orientation d by dx, wedge d by dy, and this is equal to, so the orientation on TS1 we have chosen it to be d by dx, and the orientation on n s1 over m has to be chosen such that we have an equality of orientations. So this implies the orientation we have the orientation on n s1 over m at P1 is given by d by dy. So dy at P generates the normal bundle, and we choose d by dy. So similarly, we have 0 ds1 ds2, sorry, and once again we want so on TS2 the tangent direction we have chosen is of the type lambda 1 d by dx plus lambda 2 d by dy, where both lambda 1 is positive and lambda 2 is positive. This is clear by looking at the picture, and we have wedge something So this implies that the orientation on n S2 for m at P1 is given by minus d by dx. So we have given an orientation to the normal bundles of S1 and S2 restricted to S, at least one component S of S, which is P1. So the orientation on N S over M, which is equal to N S1 M restricted to S, direct sum N S2 over M restricted to S, is given by is d by dy wedge minus d by dx, which is equal to d by dx wedge d by dy. And using the orientation on the normal bundle of S, we give an orientation on Ts at P is given by, so in this case Ts at P, the orientation on Ts at P is just going to be a sign. So we want d by orientation on M. Okay, so determinant of Tm, decimal effect 2, restricted to S, determinant of Ts restricted to S, well, determinant of Ts, tensor or exterior, N S over M. So here we have, this is d by dx wedge d by dy, decimal effect 2, a sign here, times d by dx wedge d by dy. So this implies P1 is given the sign plus. So now let us compute the orientation at P2. So perhaps this is a bit misleading when instead of writing dx and dy, because these are tangent directions, I should have taken d by dy and here d by dx. So here the local picture is d by dy, d by dx, is P2, this 2, and this S1. So once again, first we compute the orientation on the normal bundle of S1. So d by dx wedge d by dy is equal to so the tangent orientation on the tangent bundle of S1 is d by dx wedge something. So this implies orientation on NS1 restricted to P2 is given by d by dy. Next, let us compute the orientation of on ns2 over m restricted to P2. So for that we have d by dx wedge d by dy is equal to, so the tangent direction, the tangent bundle of S2 is given by lambda 1 d by dx plus lambda 2 d by dy. So here lambda 2 is negative and lambda 1 is positive. With something. So since lambda 2 is negative, so this implies orientation on n s1 s2 is plus d by dx. Okay, so this implies orientation on NSM is d by dy wedge d by dx. And finally, we have determinant dm restricted to s is equal to, so yeah, determinant ds wedge determinant ns over m. So here this is d by dx wedge d by dy is equal to sine into d by dy wedge d by dx. This implies P2 has a negative sign. So thus the class of S1 intersection S2 is equal to eta S1 fetch eta S2, and this thing, this S1 intersection S2 is 2 points, but they have this opposite signs. So there's P1, so this is just class of a point minus class of a point, which is 0. So this is of course consistent with the fact that S2 is homotopic to S3. So this is S2, and let's take a smaller circle S3 which does not meet S1, and so class of S2 is equal to the class of S3. Right, so here there's a small exercise which needs to be done. If S1 and S2 are homotopic, so let me rephrase this. Suppose we have a map from y cross r to m such that y cross 0 and y cross 1 are embedded submanifolds. Compact oriented submanifolds. So also assume M is oriented. Then the class of y cross 0 is equal to class of y cross 1. So however, so in the smooth category, points can get if we have two submanifolds S1 and S2 of complementary dimension which intersect transversely, then the points can get a plus or minus sign. However, in the complex case, this cannot happen. However, in the case of complex manifolds, the orientation is on points on S1 intersection S2 is always positive. So this is of course when S1 and S2 meet transversely and have complementary dimensions. So finally, let's prove Bezout's theorem. But before that, given a hypersurface in P and C of degree d, its class is alpha times the class of a hyperplane. To compute alpha, it suffices to intersect this hypersurface with a general line. So we will intersect it with a general line, and the assumption we'll make is assume that this intersection is transversal. So by a change of coordinates, so we do a homogeneous change of coordinates. We may assume that the line is given by the equations x2, x3, xn equal to 0, where these are the homogeneous coordinates. On P and C. Then HD, when we put x2 equal to x3 equal to up to xn equal to 0, reduces to a degree D equation in x0 and x1. This has D distinct solutions. Thus, alpha is D. And Bezo's theorem that HD1 and HD2, P2 curves in P2 of, so these are two hypersurfaces in P2 of degree D1 and degree D2, D1 and D2. Assume that they meet transversely. Then they meet in D1, D2 distinct points. And the proof. So we just need, the number of points is going to be counted by the intersection, the class of the intersection, eta h d1 intersected h d2, because all points come with a positive sign, but this we know is eta h d1 which eta h d2, which we know is d1 d2 times the class of the hyperplane, which the class of the hyperplane, which is equal to d1 d2 times class of the point. So we will end here.